Right, so the next talk is by Dr. Paul Northrup from Stony Brook University. So he's a research professor in the Department of Geosciences at Stony Brook. He leads the Tender Energy Microspectroscopy Consortium, which is a partner user program at the NSLS2 TES beamline, which is in support of Earth, Environmental, and Planetary Sciences. So the title of his talk is Exploring Geochemistry with Tender X-ray Microspectroscopy from the Critical Zone to the Deep Earth. Okay, Paul, would you like to take over?
So we're all set. Okay, so I'm going to present more of an overview of some tools, some familiar tools in an unfamiliar energy range for many of you. And I want to introduce the Tender Energy Range and some examples of using the tender energies for explorations of geochemistry. So what is the tender energy range? It's not specifically defined, but it's approximately between 1 and 5 kilovolts. And it's in between the soft, less than 2 kilovolt, and hard, greater than 4.5 kilovolt energy ranges. Historically, less work has been done in this area, so there are many opportunities. And that's what I hope to highlight today. In general, soft or hard X-ray beamlines are each optimized for their particular energy ranges. And although these can often reach partly into the tender energy range, there are in fact only a few dedicated tender energy microprobes available for use. And that's important because the tender energy range has its own set of requirements from the source to optics to the sample to the detector. So it's really important to optimize for that energy range. As shown on the bottom here is an X-ray fluorescence map of calcium, phosphorus, and potassium of a rock thin section. And the red crystals are pyroxenes, the blue areas are potassium feldspars, and the yellow in the middle is an apatite grain, which is calcium and phosphate, so it shows up as yellow. So these are the types of measurements typically made at tender energies. So why is the tender energy range useful? Mainly because it provides unique access to the K edges of geochemically important light elements, specifically from magnesium through calcium. These are very geologically important elements, and there's no way to access the K edges without going to this energy range. It also provides advantageous access to L and M edges of heavier elements, such as cadmium, strontium, molybdenum, and uranium and platinum. Applied in this energy range for a microprobe include the standard tools for a microprobe, XRF imaging and elemental mapping, such as the map on the previous slide, microbeam XANES and XS for element-specific chemistry and local structure in crystalline or non-crystalline materials. On the right of this slide, there are examples of XANES spectra for phosphorus and apatite, potassium in a clay, and uranium in calcite as examples. Another important tool is speciation imaging, where we map the distribution of different species of a given element. For example, mapping different oxidation states of sulfur or molybdenum. The measurements using microbeam XS provide much more structural information on the local scale. Typically, interatomic distances out to less than 10. In this example, the map at the top shows a very thin vein of sulfide in a silicate matrix. So the very small red rectangle pointed to by the arrow is a 4 by 8 micron beam footprint. And we use that to measure the sulfur excess of this sample. And that's shown in the middle 3 plots. Essentially, we were able to obtain the sulfur metal distance and second and third neighbor distances. And so we were able to identify this as a pentlandite. The usefulness of XAFs is that it can identify phases where microdiffraction may not be able to identify them. So it's very useful. On the bottom part of the screen, there's an example, a similar example of phosphorus XFs. So phosphorus can be studied in the same way in this energy range. So overall, there are a lot of potential applications for tender energy microspectroscopy in earth sciences. Just a brief list here includes critical zone environmental and soil biogeochemical processes. In particular, phosphorus is an essential nutrient, but can also be an important environmental contaminant. Sulfur in soils and sediments is a key participant in redox and biogeochemical processes. Climate change will impact many critical zone processes, and this feeds back on climate through nutrient cycling and carbon cycling. The geologic record of paleoclimate is also present in, it's recorded in sediments and in biominerals. Tender energy microspectroscopy is also useful in mineralogy and crystal chemistry, particularly in trace element studies, and most notably in carbonates, where you can go below the calcium absorption edge. So you can see everything below calcium without interference. And this is very important for carbonate geochemistry and geochronology, and it also relates to isotope studies. In igneous petrology, we look at magmatic processes and redox processes in these systems. Excuse me, sorry, I lost my voice. This is also very important in economic geochemistry and ore mineralogy, particularly relating to technologically important metals, such as rare earths. And in geophysics, we can look at high pressure phases and use that to study planetary science. And in marine biogeochemistry, a number of users are looking at such systems as mid-ocean ridge hydrothermal systems and in nutrient cyclings and particle chemistry. So the first example is one of the prime examples of this energy range, looking at phosphorus in soils and sediments. The speciation of phosphorus is highly heterogeneous at the grain scale, as a number of presenters today have mentioned. The speciation, however, determines the bioavailability of phosphorus for agricultural and ecological productivity, as well as carbon sequestration. The speciation also determines the leachability of phosphorus, potentially from large reservoirs that could lead to pollution of ground and surface waters. These materials have a very complex response to redox processes that also involve iron, sulfur, and manganese, and are very importantly perturbed by climate change events such as flooding and seawater inundation. And those have very, very strong impacts on the local grain scale chemistry of phosphorus, sulfur, and iron. These materials are not really well understood using bulk methods. Bulk representative of the important grain scale processes going on. So microspectroscopy is an ideal tool to study the grain scale phosphorus chemistry. Looking at some data, this map shows the complexity of phosphorus in a soil, in a typical soil. Phosphorus is shown in red, sulfur is in green, silicon is in blue. So you see a number of silicate grains. The sulfur hotspots, all of the green particles are mostly organic matter, bits of organic matter. And the different red spots are high phosphorus, and they're highly heterogeneous. The right is a grain of apatite mineral, and the more fuzzy diffuse area pointed to at the left is an area of phosphate adsorbed to ferrohydrite. And if you look at the different Zane spectra and the examples of standards on the upper right, the structural details of the spectra are very diagnostic of different species of phosphate. And so the position of the peak and the associated pre-edge and post-edge structures are very informative and allow you to identify the phosphorus species. And most soils have quite a variety of different species present in them. And these participate to varying degrees in the overall phosphorus chemistry and reactivity of it. In another example, there's a large map to the left and then the close-up of one spot on the right. And this shows that there's a co-location of phosphorus with aluminum, which is a clay material coating a silicate grain. And this was confirmed with phosphorus zanes, which showed that it was phosphate adsorbed to an aluminum mineral. We also did correlated mapping of this same sample at a hard X-ray microprobe and saw that it was also co-located with iron and manganese, but the phosphorus zanes showed that the phosphate was associated only with the aluminum in that mixed post phase. So that's where the phosphorus zanes is very useful for identifying the chemistry. On the biological side, looking at sediment that has been redox cycled in a wetland, we also see a contribution from organic phosphonate. And phosphonate is a phosphorus species with a phosphorus carbon bond. And of the 3 spots that are analyzed on this map, one spot is an apatite grain, and the other 2 are organic phosphate, mostly phosphonate species. Switching to a neighboring element in the periodic table, sulfur is a very useful element to analyze. Its oxidation states are many and varied, and they're spread out over a wide range of energy, so you can distinguish between them very well. This example is an example from a magmatic system. It's a synthetic product quenched from a high pressure run that has a glass matrix and various small crystallized mineral grains. In this case, we did speciation mapping. So 8 grains are shown in green, and both were precipitating from this melt. And the small blue dots are high in phosphorus. Those are apatite crystals. Then we went in and did microbeam zanes of each of these phases. And you see that on the right, that each of these phases has a very different combination and or mixture of sulfur species in them. Also on the subject of sulfur, but throwing in some associated elements, including aluminum, magnesium, and chlorine. We looked at samples of precipitates that formed beneath the Antarctic ice sheet. And these record conditions over approximately 6 million years of time. And these precipitates were studied using tender energy techniques that were critical to identify some of the geochemical processes that created these sediments. Mostly they're carbonates and silicates and sulfates. So we're able to find minerals that we did not expect there, and this was able to tell us a lot about the geochemical fluids and processes and how they change depending on the climate and the thickness of the ice sheet above it. So this is kind of an extreme example of low temperature geochemistry. It's about -5°C. So that's very much low temperature geochemistry. While on the subject of carbonates, it's important to think about uranium because that's quite often an important trace element in carbonates and much of interest, particularly for geochronology. And the uranium M5 absorption edge is at 3,550 eV. Distinct advantages when compared to the more typically used L3 absorption edge at a much higher energy. One of which is the sampling depth is comparable to the beam size for a microprobe. So the horizontal and spatial resolution is not degraded by thick samples. Typically, microprobes operate at 45 degrees. So if you have a 30 micron thick thin section, you're sampling all 30 microns looking at the uranium. That is not the case for the M edge, where you're only sampling a few microns and you get much sharper and spatial resolution. The M edge zanes can also very clearly identify oxidation state, typically much easier than can be done at the L edge. The M edge has an extremely sharp peak, and it's very sensitive to oxidation state. And we've used that down to the ppm level, a single ppm level of concentration. So that's very useful. Looking into economic geology and rare earth mineralization. This is a study that looked at yttrium, which goes along with the rare earths, as well as sulfur, silicon, and uranium. And on the left, you see a map that includes the yttrium L edge, silicon K, and uranium N fluorescences. And the red line in the middle there is a rare earth yttrium carbonate mineral. And a close-up, an extreme close-up of that done at our highest resolution shows there's also sulfate in the neighborhood, but it's not participating in with the carbonate mineral. And there's also uranium, but that's present in fluorite, which is associated with the carbonate. This study was made possible at this resolution because we're operating below the calcium K edge. So we're not seeing the extremely high calcium signal. And the last example that I want to talk about is an example of shock melt of minerals. Minerals can be melted in place or rendered amorphous by a pressure shock wave. And different minerals or compositions of minerals can be affected differently. And this image shows feldspar composition grains from a simulated impact site. But potassium zanes shown on the right, the blue spectrum, demonstrates that the local structure is amorphous. It's not crystalline. The red plot is an example of a standard feldspar potassium zanes. So this can identify amorphous versus crystalline phases. And the potassium zanes showed the same effect. So overall, I hope that I've shown a variety of examples that illustrate that there are many opportunities for tender energy microspectroscopy in our sciences. And it's another tool or a bunch of tools that can be used for geochemical studies and hopefully pique some interest and get some science. I'd also like to acknowledge the many users and collaborators whose work I've shown, and of course, NSF and NASA for the funding. Thank you.